And today, I think it's about peptide design.
Can you hear me? Yeah. Yes, so today, is it working? So yeah, today I will talk about peptides. Actually, it's a project we started, I think 1 year ago. The idea was at IKTOS, we develop methods to generate molecules, to evaluate small molecules. We work on retrosynthesis and generative AI technology. We wanted to see what we could do with peptides, and not just simple peptides made of just natural amino acids and linear peptides, but also more complex peptides. So we started working on that, and this is the work from Massina, Abderrahman, Nicolas Deveau, and Mo Juzos that I will show today. So, okay. So let's talk about quickly about peptide in drug design. Very quickly, some numbers. Actually, peptide is not the main field in the pharmaceutical market, but they represent about 5% of the market. We see an increased number of peptides in the clinical development today. So today we have around 80 peptides in drug market, 150 peptides in clinical development, and many more in preclinical. Main limitations we see on the development of peptides is they must be delivered by injection because they lack some good properties to pass the membrane and some oral bioavailability. Also, one of the reasons they cannot cross the membrane, so mostly they target protein in the peripheral extracellular targets. So if we now look more at the kind of peptides we find in the clinics, if we look at the length of this peptide, we can see that at the beginning we are more in the small peptides with an average length of 9 amino acids. Now we are growing bigger with 119 to 20. It seems to stabilize a bit around this value. And they don't just grow bigger, they also become more diverse. As I said, we don't look at just natural amino acids. There are modified amino acids and some heavily modified, like some tails that are plugged to them to improve their permeability, for example. There are also some linking, so we know the disulfide bridges, but there are also many other kinds of bridge, meaning that we have cyclic peptides and not just from head to tail, but also from internal linking. So it makes these molecules actually quite difficult to study. It's not possible to just apply methods that rely on the sequence of the peptide. We need to find about new way to represent these peptides. Maybe the representation we use typically for small molecules are not so well adapted. That was kind of the question we wanted to ask on this project. So we looked at what we could do. So our goal was to build and evaluate predictive and generative models for peptides. We wanted to be able to take into account these complex peptides, which includes modified amino acids, cross-link, linkers, etc. So first of all, the question we need to ask is what kind of representation is adapted to these peptides? So classically for small molecules, we come from the small molecule field. Everybody here knows about the classical representations that are used for small molecules to train machine learning models. They rely mainly on two things, on physical chemical descriptors, but also on molecular fingerprints. So actually, Matthias this morning talked about ECFP, so I won't go into the detail. Just I wanted to mention that because the way we build these molecular fingerprints based on the cyclic representation is actually quite interesting. And our first idea was maybe we can reuse this way to compute fingerprint from the graph of a molecule for peptides in a different way. One important thing in this ECFP and Morgan fingerprints is the atom invariant. The way we define that, define what is unique in a molecule, and this combination leads to the building of the fingerprint. So what we wanted to see is, well, compared to these classical methods for small molecules, can we propose some different representation? And we wanted to have a more coarse-grained representation of the peptides that take into account the fact that we start from amino acids, although they can be modified, they can be linked. The question is, can we have another graph representation of this peptide that take into account this specificity. So we started by building very simple peptide graphs, where each node corresponds to an amino acid. Each bond is normally a peptide bond, but it can be also a disulfide bond or something else. And then we also wanted to have a different version in which we split the amino acids in two parts, the backbone and the side chain. And the idea is maybe we can associate some properties to the side chain that is different from the backbone, and maybe this representation could be a bit better compared to the first one. So to do that, actually, we use an algorithm to detect the amino acids in the sequence. So in general, we start from a smile of the molecule. So we need to identify each amino acid. So we use Proteax, which is a German company who developed this PLN format. So it's actually helped us to convert the smiles into the list of peptides, of amino acids. And then with this graph that we build from the amino acids or with the backbone side chain, we wanted to convert this graph into a vectorial representation using the same Morgan fingerprint that we apply on this graph. So we need to talk about invariant also for this peptide. So in that case, we tried two very simple ideas. The first one was to take just the amino acid name, so like tokens, it can be a proline, etc. So all the amino acids are considered different from each other. Or we could have some kind of amino acid descriptors that represent the invariant, meaning that two amino acids that would have the same molecular weight, rotatable bond, TPSL or P, and charge would be considered in the same invariant. So we test these two versions. So it was just to see whether this representation, this new representation, could maybe in some cases be better compared to the classical Morgan fingerprint or vector of descriptors. So to evaluate this method, so we just finished. That's just a summary of what we have. We have this AA representation with tokens, AA with descriptors, backbone sidechain with tokens, and backbone sidechain with descriptors. So next step is to compare this representation with Morgan on atomic level and molecular descriptors for classification tasks. So to do that, we use actually two different data sets in a collaboration with two pharmaceutical companies. The first data set is peptide that has been measured on two different targets. Sorry, I cannot say the name of the target, so we'll call them target 1 and target 2. The information here is that we have 189 small linear peptides, all measured on both targets. And these peptides include modified amino acids and other specific components. It was mainly some linkers that were added to the peptides to increase stability and permeability. And just a distribution on the two targets. So you see that we had, let's say, a quite well-balanced data set on the two different targets. So we trained some machine learning models. Here I'm showing the results on the random forest. And we evaluated on this data set the different methods that we had. So Morgan fingerprints, molecular descriptors, and all the different new representations that we had. Two different versions of the backbone sidechain descriptors. We just changed the value of the invariant. And what we can see is when we do either random split or stratified single linkage split, so stratified on the activity, we were actually able to reach good performances with the new representation, although, as again, and I would say, as almost always, Morgan fingerprints still have very good performances on this data set. However, when we do a more difficult split, we've seen that maybe increase in the difference of the performances of the new methods, although all the methods decrease in performances. On the second data set, we had some similar results. Maybe the Morgan were a bit better for the random split, but in that case, we completely lose the predictive power of the Morgan when we do stratified single linkage split. In that case, we've seen that, for example, backbone sidechain descriptors perform quite well on this data set. The second data set we use come from a second pharma company. The goal was to predict peptide permeability. And actually, the data set was much bigger with 5,000 peptides. They were both linear cyclic peptides with measured permeability. So in that case, we had only modified amino acids and linear or cyclic peptides. So you have an overview of the size distribution of the peptide. So actually quite large because we go from 4 to 11, but most of them were between 6 and 9. And if we look at the distribution in cyclic and linear peptides, actually most of them were cyclic peptides. So here, when we trained the models, our idea was also to look at, of course, the random split to see the performances. And again, Morgan fingerprint on the atomic representation still performed quite well. However, when we try to do some kind of transfer, let's see, we train the model on cyclic peptides. What happens when we predict for linear ones? Here, for example, Morgan is not able anymore to predict. Maybe because of the representation of the atomic, how can I say, the cyclic bonds that are difficult to interpret, and certainly the similarity between cyclic and linear peptides is quite different in terms of Morgan. As we can see, for example, here, the backbone sidechain tokens perform quite well, although not so good, I would say, better than the other methods. Surprisingly, compared to what we've observed previously, the molecular descriptors perform well in the other sense when we train the model on linear peptides and predict for cyclic ones. And then again, we did the same thing for small versus large, large versus smalls, or for just specific sites that were quite crowded. And as you can see, in the end, it's quite difficult to say that one method outperform the others. It seems that depending on the case, some methods seems to better take into account the differences between the peptides. So I think it was still an interesting work to do on this data set to check whether new representation, new way to represent the molecules can bring different results, maybe sometimes better results compared to the classical Morgan fingerprints. So the next question for us is, okay, now we have predictive model for these peptides, but can we generate new peptides and use this generator to these predictors to guide the generator? Because that's a technology we already have for small molecules at IKTOS. We use a classical LSTM generator that we optimize with reinforcement. So the difference is, instead of a classical smiles for LSTM, where we write the character of the smiles, we use the PLN representation, meaning that we train the model with the amino acid names. So we just have to generate a new sequence, a new list of amino acids to build a new peptide. The PLN representations allow us to have cyclic peptides. They have a notation that is similar to the numbering in the smiles, and with that we can actually generate as many new peptides as we want. The key element here is how we train the generative model to generate new peptides. Actually, we created a random database of peptides based on the frequency of amino acids in the initial dataset. So we just randomly sample peptides, and we use that to train the LSTM generator that we then use to reinforce using our predictor. So in our case, the predictors was the different predictors that I've shown before. On top of that, and that's one of the good things with this kind of generator, we can add other metrics during the generation that we can optimize at the same time. It can be similarity to the initial dataset, it can be quality scores, anything that we want. And that's typically what we did for some of the generations. So as you can see on the first project, we evaluated the scores of the generated peptides using the predictor. So here you have the different steps of the generator. Each time we do a round of generation and prediction, and we score about 100 peptides at a time, and we look at what is the score for the target 1, target 2. So what is the score for the best peptide in the batch? And we see that we are able to climb the different score actually quite quickly. We also had some metric on the similarity of to the initial data set, and the final score, which combined all the score, we were able to actually optimize it during the generation. So it was a good demonstration for us that we could use this representation, this PLN representation, to generate the peptides and score them on the predictors we built previously. Now, if we just have a look at the distribution of the amino acid in the peptides, if we compare the initial data set with the active peptide and their composition in amino acids, we can see that actually we are quite close to the in the generated peptide, the ones that are predicted active. There are some differences, for example, here or here, but actually it's not major differences, and that's typically the kind of thing the generator do. We try to just optimize the peptide, but by staying in the applicability domain, we control that with the similarity mainly. On the second data set, we generated also some peptides satisfying the constraint with some target that we had and additional quality score. So we actually wanted to add different scores based on the feedback we had from our colleagues. And so on the main target, we had a good evolution of the scores. We've been able to also add some IP space scores that they help us build, some ID on the isoelectric point, because it was one of the things that our collaborators thought was important for the peptides. Also, they had some rules for synthetic access. So we wanted to check whether the peptides we generated could match these predictions, and same thing, for example, for the solubility. So in the end, we've been able also to climb the different score with the LSTM using this PLN representation to generate them, and these different predictors that use the representation we've built. Again, if we look at the distribution, it's quite similar to what we observed for the first case. We are able to stay to reuse the different amino acids that compose the most active peptides, maybe just in a slightly different way. We stay actually quite close to the initial data set, but we believe that some of these peptides have actually nice properties, and some of them may be synthesized by our partner. So to conclude on that, we introduced new graph representation of peptides at different levels, atomic level or amino acid level, and an intermediate backbone sidechain representation. These graphs are then converted in a vectorial representation using the Morgan algorithm. We compared this new representation with classical Morgan fingerprints on atomic graph and with molecular descriptors in different classification tasks, and we obtained actually promising results on two different data sets depending on the splitting scheme. And we use these predictors to generate new peptide with optimized predicted properties. So that's it for today. It's actually an ongoing work at IKTOS. It was really mainly a proof of concept for us, but it's a field that we are interested in. And just to finish on that, so otherwise at IKTOS we developed two main technology, a technology for deep generative modeling for small molecules, and a retrosynthesis tool, and you can try it for free, so feel free to do it. Thank you very much.
Okay, thank you. I think you have time for one question, one or two.
What activity did you speak?
For which one? For the.
I mean, you mentioned that you optimize property. Which property did you optimize?
So we optimize solubility. We optimize synthetic access. They had a list of rules that they wanted us to apply. For example, some amino acids cannot be close to each other, or we don't want to have too many glycine, for example. So these were rules that we coded, and then we just wanted to check the number of rule violations that we had. We wanted to limit this rate of rules violations. So that's typically the kind of thing. On top of that, we had a similarity to the initial data set, so that we don't generate a peptide that is completely novel with just new amino acids that should be out of the applicability domain of the predictors.
Can you hear me?
Yes.
Thank you for your talk. I have a question concerning your data set for the generative models. How big are they? Yeah, this slide. So you said that you have a peptide database.
Yeah.
Could you just tell a bit more about this database and like the?
Yeah, so I think we had around 1 million generated peptides here. So again, these are not real peptides. These are fake peptides that we randomly generate from the list of amino acids that are present in the initial data set, and that we combine randomly, just respecting the proportion of each amino acid in the initial data set. So the idea is just to show plausible peptides to the generator, but then we transfer this generator on the initial data set. So at that time, we show real peptide containing the same amino acids, but that come from the data set. And after that, we are able to reinforce on the predictors to increase improve the properties of the peptide we generate.
Okay, thank you so much.
Hi, thank you for your talk. I understand that you compare different sets of features to do the machine learning for the classification task. I'm just wondering if that's going to be any better if you combine like the graph, your new graph fingerprint and the different molecular descriptor tools all together.
Yes, actually, we tested that to combine the different descriptors, so combine the new representation with physical chemical descriptors. We haven't seen some improvement on the performance. It was quite the same, but we haven't tested to combine both Morgan on the atomic level plus the Morgan on the peptide level, amino acid level. So for that, that's something we could test, but with physical chemical descriptors, we couldn't see an improvement. For small molecules, we often see improvement when we combine them. On this dataset, at least, it was not the case.
Quick question. So you mentioned that you cannot have many glycines in peptide. Question, why?
Well, actually, these are some rules that our collaborator suggested to us. I'm not sure why it's an issue.
Because you're going to break alpha helicity, that's why. That's what you should add in the model, that when you generate randoms, you're assuming they're alpha helical, unless you're working on cyclic, which you're not always. So when you put too many glycines, it breaks it. Okay. Yeah, and I published the first ever paper in 2005 on this. Okay. I invented this. So you just have to add just one little routine that you watch for alpha helicity, because sometimes it's violated.
Okay, I think this was the last question. Thank you. And I think we'll thank all the speakers again.